test the microphone. I think so. What? Not on the camera, no. Still, it's funny.
Liru.
67 people. Oh, it's gonna be Luke Robitaille this time.
Oh, I got a meet.
So, hello everyone. We'll be starting soon. Okay, everyone. Okay, so, all right, so it's recording. So it looks like we're good. So just to be sure, can you all hear me?
Yes.
Okay, good. Okay, so hello, welcome to our Math Divulged class today. And this is the intermediate class, so harder than the introductory class, but we're actually trying to help you do well on math contests as opposed to the seminar series, which is just like neat math that may or may not be relevant. And so today's topic is inequalities. And a lot of times this class, the intermediate class, is maybe thought of as trying to help you with the AMY. But as you know, the AMY, the online AMY was last Saturday. So, giving you AMY prep now would be, a bit late. And the USAMO and USAJMO online are scheduled for a little over a week. So now seems like a good time to maybe focus a little more on preparing for Olympiads, especially because inequalities are sort of a more Olympiad-y type of thing than they would be more of a computational type of thing. So maybe today's class will be a little more geared toward Olympiads, and the handout probably also, there will be a lot of problems on the handout. Don't feel like you need to do all of the problems on the handout, but this might be a little more Olympiad-y than usual. Maybe it'll be harder than usual, but don't worry, just hang in there and we'll do some cool math. Okay. And so you can, if you have questions, please message the TAs, Eric or Naveen, not me. Don't message me with questions because then I would we have people to answer your questions for you. It's more efficient for me to just keep lecturing and for the TAs, answer questions. Okay. So you can message your questions to Eric or to Naveen, the co-hosts, basically. So I guess we'll start very shortly. Okay, so yeah. So yeah, questions to Eric or Naveen, not to me, and so I guess we'll get started. So inequalities. So, an inequality is basically oftentimes, on some math Olympiad, there will be some problem that maybe is like, prove that this is greater than or equal to that. And or prove that this is less than or equal to that with some, algebraic expressions or something. And so, yeah. And so, and then you have to have some techniques to prove them. And so you can sort of build up a lot of inequalities from some simple ideas. So one of the basic building blocks of inequalities is the trivial inequality. The trivial inequality the trivial inequality basically states that if you have any real number x, then its square is non-negative. And I think that this is pretty obvious. In fact, it's even called the trivial inequality. Basically, the idea is that if x is negative, then its square is, if x is positive, then its square is positive. If x is negative, then its square is positive. And if it's 0, the square is 0. So you get this in all cases. And furthermore, the only case in which you would have equality is the case where x just equals 0. And it does hold in that case. So equality, oftentimes when we do equalities, we might wonder, what is the equality case? When does the greater than or equal to sign maybe turn into an equal sign? And so in this case, the equality case is just when x is 0. And you can see that, 0 squared is 0, so it does hold. Equality does hold in that case. So that's the trivial inequality. Now, you might be surprised that, there are actually some problems that you can solve with just some massaging algebra around in the right way. And maybe you use the trivial inequality, or maybe it just falls out of the algebra. But there are some more theorems that are true that can be useful. And so one of those theorems is the Mgm inequality. So the Mgm inequality says that, and I'll show you more examples of, I'll be doing examples of problems using this stuff. Don't worry, we'll have plenty of examples. So the Mgm inequality basically says if you have, I guess, some non-negative real numbers, a1, a2 up to an, where n is a positive integer, then their arithmetic mean, which is basically what you just get if you add them all up and then divide by how many there are, basically just what you might call the average, is greater than or equal to their geometric mean. Basically the product divided, the product, and then you take the nth root. So this is obvious, the trivial inequality is obvious, but I think this is not obvious. We would not call this trivial. So let me show you how you would prove it. And let's start with sort of one of the most important special cases, which would just be when n is 2. So n is 2, and in that case, this would just say, in this case, I'll just call the numbers a and b. This says that for non-negative reals a and b, we have this. So how do we prove this? It turns out this is equivalent to the trivial inequality because both sides are non-negative. But both sides of this inequality are non-negative, so it will hold if and only if it holds when you square both sides. Basically, if we prove this, then we have shown this because you can take square roots of an inequality of non-negative reals and it still holds. And conversely, if this holds, you would have this, but we only need the direction going up. So we need to show this. This is equivalent to if you just multiply through by 4 to get rid of the 2 in the denominator, the 2 squared. So we need to show this. A plus b squared is at least 4ab. And now, look, this, expand the a plus b squared and you get this is what we want to show. But you can see that this is true because this is the same as if we said this. And behold, it's the trivial inequality because this expression is a minus b squared. This proves the Mgm inequality when n is 2. And it also tells us about the equality case because, if equality held here, then it would hold here, so here, so here, so here. And then, we would need a plus, for equality to hold, that would be if and only if a minus b is 0, which is if and only if a equals b. So equality holds if and only if a equals b. Now, that turns out to be the equality case in general, which I will state also. The equality case is when they're all equal. You can see that this is an inequality case. If you have a bunch of copies of some number x, then the arithmetic mean of a bunch of x's is x. The geometric mean of a bunch of x's is x. So you just get, x equals x. And so it would be an equality case. So let's prove this in general. So we're going to proceed by induction on n. So basically, induction is when you prove something for a base case, like it's sort of akin to climbing a ladder. To climb a ladder, you need to get on the first step, and then you need to go from each step to the next. And so we're going to induct like that. And also, so we showed it for n equals 2. It's obvious for n equals 1, you would just get this. So we have it for n equals 1. So let's suppose that we're going to induct on n. So let's suppose n is greater than at least 3, because we have taken care of those already. So we can assume n is at least 3, and then we want to show that if it's true for n minus 1, then it's true for n. So consider the following. Basically, let m be the arithmetic mean. So what we need to show is that m is greater than the geometric mean, which, since everything is non-negative, it's equivalent to showing that the product is at most m to the n. So what we're going to do is basically, the idea is that intuitively, if you have two numbers and their sum is fixed, then the product increases as they get closer together. Like, the product of these two numbers is less than the product of these two numbers. It's less than those, etc. So what we're going to do is, this is very symmetric. So let's just assume, without loss of generality, that A1 is the largest. So if A1 is also the smallest, then, it's obviously done. Because then they're all equal and it's trivial. Otherwise, some other number is the smallest. We can take another number that's the smallest. So let's say it's A2. Like, if they're all equal, we have equality. Otherwise, we can take one, the smallest isn't equal to the largest. So we can assume that A1 is the largest and A2 is the smallest. Without loss of generality, I mean, sure, you could have that A14 is the largest and A57 is the smallest or something. But this is like, the sum doesn't change when you reorder them. The product doesn't change when you reorder them. So we can just, by symmetry, assume that that's not the case. That they're not, like, that we just have the largest one here and the smallest one here. So we said if they're all equal, it's equality. And I'm going to show that in any other, assuming that's not the case, when we took one that was the largest and then that wasn't equal to the smallest, so a different one was the smallest, I'm going to show that, in fact, we have a strict equality. So here's what I'll do. First of all, notice that A1 is at least the average. You can rigorously prove this, but this is just obvious. Basically, what this is saying is that the largest number is at least equal, or actually, since they're not all equal, it's strictly greater than the average. Like, I think this is kind of obvious. What this is basically saying is just, if you have a bunch of numbers, then and they're not all equal, then the largest number is strictly greater. Notice this is not a greater than or equal to sign, it's just greater than, is strictly greater than the average, the arithmetic mean. That's pretty obvious. Oh, maybe you can't, I'll read that. Wow. There, I think that's better. Okay. So yeah, this says A2 is min A1 through AN, as Eric pointed out. Thank you. Okay, and similarly, we have that the smallest is strictly less than the average. So what I want to do is consider the product A1, A2, and the product M A1 plus A2 minus M. What we're basically going to do is take these two numbers and then replace them by moving them closer together by replacing one of them with M. So how do these numbers compare? Well, their difference is this. And if you notice, this factors like this. This is positive, this is negative, so the product is negative. So when the difference is negative like this means that the original thing, that this is less than that. So we know this. Now, if any of the numbers are 0, but they're not all 0, then this product will be 0, and but m will be positive, so it'll be strict. So assume none of them are 0. Then, when I multiply this by all the rest of the numbers, I would get a1, a2 times a3 up to an is less than, since this is positive, since we said none are 0, is less than this. And this is a non-negative number. This a1 plus a2 minus m is non-negative, clearly. It's positive. Yeah. So now, this is what we're going to do. Look at these n-1 non-negative real numbers. This is non-negative because it's a2, which is non-negative, plus a1 minus m, which is positive. So now look at these numbers. a1 plus a2 minus m, and then all the rest of the ai's, a3, a4, a5, up to an. We have n-1 numbers here. Let's apply the smaller Mgm to them, which we said is true by the inductive hypothesis. Okay, so what is their arithmetic mean? This is the cool part. Their arithmetic mean is just m. And you can just see this, because like, when the arithmetic mean of all these numbers was m, when I do this operation to change that to this, the sum doesn't change, so the arithmetic mean doesn't change. And then like when I have a number that's equal to the mean, deleting it doesn't change the mean. So the mean is still just m. And so by the AMGM for the n-1 case, the product of all of these numbers is at most, the arithmetic mean to the n-1 power by, just raising to the power. Like if you formally apply, we get the m-1th root, the n-1th root is at most the arithmetic mean, which is m. So we can raise to the n-1 power, because n-1 is positive, sure. And so that preserves this. So we know this. Since none of them are 0, we said, then m is positive, because they're all positive. Okay, so multiplying by m, we multiply this by m. And we're done. Just glue these together, and you get this. Glue this inequality together with this inequality, and you're just done. And we get this. And so, yes, we're done. We've proved the Mgm inequality, and we proved that equality holds if and only if the numbers are all equal. So the induction might have sort of obscured what was really going on here. But to sort of put it in a nutshell, what we basically just did is, if you have some numbers and you want to show that their arithmetic mean is at most the geometric mean, basically what you do is the arithmetic mean is at least the geometric mean. Basically what you do is you push, the idea is just push them closer together while preserving the sum, sort of intuitively. And what we showed that this sort of intuitively, you showed that it sort of increases the product, basically. And just keep doing that, and then you've increased the product. And then when you finish up, they're all equal, and you have that the arithmetic mean equals the geometric mean. So basically what we showed is the arithmetic mean to start with must have been greater than the geometric mean unless when we started out, they were all equal anyway. And so it was just the arithmetic mean equal to geometric mean. So that's sort of intuitively what was going on. So yeah, don't worry if you didn't follow all that. What's important to know is what the statement of AMGM is. Because basically on the Olympiad, like, by the way, this proof or some version of this proof is probably in some AOPS book, I think. But there are multiple proofs, but this one sort of gives you hopefully a good feeling for what's going on. So, right. But I think this is in AOPS volume 1 or volume 2 or something. Maybe, or something like this. Or something. And the AMGM inequality probably has a Wikipedia page, maybe. But the point is, for the Olympiad, you can just say by AMGM, da da da. The grader on an Olympiad doesn't care and doesn't know and doesn't really need to know whether or not you know how to prove AMGM. So like, it is good for your mathematical understanding if you follow that proof, but if you didn't, like you probably should read about a proof of AMGM, but like, don't despair. You can get a good score on the JMO or the USAMO without knowing how to prove AMGM. And in fact, there might not even be any inequalities on the JMO this year. Who knows how these things work, but there might be. We'll find out in, about a week and a half, I guess. But yeah, what's important is that you know the proof. I mean, not the proof, just the statement. And the equality case is good to know, but yeah, and that's, pretty simple. So yeah, this is AMGM. This is true for non-negative reals, and equality holds if and only if the numbers are all equal. So that's AMGM. Let me tell you about another inequality. This inequality is called Cauchy-Schwarz. The equality case here is pretty interesting. So Cauchy-Schwarz, the Cauchy-Schwarz inequality. Cauchy-Schwarz tells you, let's say you have a positive integer n, and then you have a bunch of real numbers, a1 through an, and then b1 through bn. So what Cauchy-Schwarz tells you, and these don't have to be positive, but they can be, of course, They're just real numbers. What Cauchy-Schwarz tells you is that the sum of the squares of the a's multiplied by the sum of the squares of the b's is greater than or equal to the sum of when you multiply each a by each b squared. Now, there are multiple ways to prove this. You can probably find them online or wherever. In fact, this follows from the trivial inequality, since it turns out that like the left-hand side minus the right-hand side is actually just equal to like this sum, aibj minus ajbi squared over all indices I and j with I less than j from 1 to n. So, and this can just be checked, and this is a proof of Cauchy-Schwarz. And in fact, this will tell us about the equality case. Because basically to have equality, we would need to have this. for all I and j. And so, so basically the equality case is either the A's are, so if the A's are all 0, then, you know, if the A's are all 0, then you've just got equality, because this is 0, 0 times anything is 0, and then you have a bunch of terms that's 0 times something, all zeros. So the equality case would be the AIs are all 0, or if they're not all 0, then you can take some AI that's not 0, and then we would have, for every j, we would have this. And like, you can check that the I less than j doesn't matter, obviously, in this equality case. And so then this, if we call this constant lambda, or there, so otherwise, or not all 0, and we have some constant lambda with this holding for every I. Bi is lambda times AI. And this will actually be an equality case. You can check this one too. And so basically that's sort of one way of thinking of the equality case. Or another way is that you could think of as like they're both proportional to some vector. Like, but there are some constants ci and some constants lambda and mu with this and that for all I. So yeah, that's another way of thinking of it. But basically, intuitively, the equality case is roughly the sequences are sort of proportional. And this is the Greek letter lambda, as I'm writing it, L-A-M-B-D-A, lambda. So another way to think of this, another proof could be basically to write down this function, ai times x minus bi squared, and then sum it over all I, and then basically note that this, like, it's a quadratic, or basically a quadratic, and it doesn't have any real roots. And so the discriminant is non-positive. And so either it's just a constant function which corresponds to the ai all being 0, or there's some value that's a root of all of them. Like its discriminant is non-positive, which gives you this. And like for the equality case, you can do the algebra and see that that's sort of what it gives you about like the discriminant being non-zero, giving you that like there's not a root, or like the discriminant being non-positive. So because like it's the sum of a bunch of squares, and so there's at most like one, it doesn't have two, if it were positive, I guess it would have two distinct roots or something is the idea. And then like if the discriminant is 0, which would correspond to equality, then either the ai are all 0 or there's some value that's a root that gives 0 for all the ai minus aix minus bi simultaneously. Sort of a sketch of another proof. But again, you for Olympiads, oh, someone asked, what about when all the bi are 0? That's covered in this case because you could take lambda equals 0. But yes, you would have equality in that case too. So but again, you should know how to prove it, but like for the Olympiad, you don't need to know. And sort of another way of viewing this is basically like if you took a vector, two vectors, like in n-dimensional space. And then this is basically just saying, like if you take the square root of both sides, this is basically saying that the dot product is at most the product of, or like it says that the dot product squared is at most the product of their magnitudes squared. Which basically boils down to like the cosine, like, which basically can sort of boil down to that. And you can find all this stuff I'm saying in books for the most part, I guess. I didn't invent the Cauchy Schwarz or the AMGM or anything. This is, you know, pretty known stuff. You should find, most of this can be in any book, I guess. And so this is sort of just saying this. Of course, to make that rigorous, you need to sort of say, well, how do you find angles in n-dimensional space? How do you know that n-dimensional geometry works at all? And so, whatever. That's one pitfall, as I've seen it explained. But like, that's sort of intuitively what this is saying. But yeah, that's Cauchy Schwarz. And another thing, something equivalent to Cauchy Schwarz basically is what is sort of jokingly nicknamed T2's lemma. I guess T2 Andrescu really likes this lemma or something. T2's lemma basically says if you have any real numbers, x1 through xn, real, and any positive real numbers, y1 through yn, then you have this, x1 squared over y1 plus x2 squared over y2, all the way up to this, is at least the square of the sum of all the x's over the sum of all the y's. Notice this follows immediately from Cauchy Schwarz, because you can just get rid of this denominator and bring it over here, because all the y's are positive. So we just need to prove this. And it just turns out, this is just exactly the Cauchy Schwarz. If you see, it just fits into the same form. Because you take ai is the square root of yi, and bi is xi over the square root of yi. And it just fits this form exactly. And so it follows from Cauchy Schwarz. You can just check because ai squared is yi, bi squared is xi over yi, and aibi is xi. So it's just Cauchy Schwarz, exactly. And so this is a sort of, this can be useful for solving problems in some scenarios. And so that's T2's lemma. And so there are a lot of inequalities that have been shown. Some of them are, some of them are really popular. Some of them are maybe more obscure. And so, like, maybe for math contests, you often, you don't need to know a whole arsenal of theorems, and then you try, if I teach you, a bunch of random inequalities, and then you're like, oh, let me use Karamata's inequality and Popoviciu's inequality and try to kill this problem with the n-1 equal variable principle, and maybe let me expand this giant expression with 192 terms or something crazy, and then maybe you don't solve the problem, and then maybe another student is just like, maybe I can solve this problem with a creative application of AMGM or Cauchy Schwarz or something. And so maybe they solve the problem. And so, like, the point is, most of the time, you don't really need a lot of fancy theorems. But you should definitely know this AMGM and Cauchy Schwarz. I will quickly mention a couple of other theorems, which can be useful occasionally. But like AMGM and Cauchy Schwarz are quite important. And actually, there's another inequality called Holder's inequality, which is a generalization of, I think the O has 2 dots over it or something, which is a generalization of Cauchy-Schwarz, but I'm not going to get into that today. AMGM has a generalization called weighted AMGM. Not going to get into that today. That you can also look up Bernoulli's inequality, which can be useful for things. But let me tell you quickly about a couple of other, or one other inequality I'll tell you about briefly is the rearrangement inequality, which basically says, say I have two sequences of numbers, x1 through xn and y1 through yn, and they're in increasing order. Then it basically tells me that, suppose I want to pair up the x's with the y's. And then like take the product of each of the pairs you made and then sum up all the products. So basically what rearrangement tells you is that the best way to do it is just sort of to pair them up in their order. So basically it says that like this holds for, I guess, if you want to think of it this way, for any permutation sigma of 1 through n. And as one of the AOPS books explains it, this is really quite intuitive. Basically, imagine you go on a game show and there are some boxes on the stage. One of the boxes has a bunch of $100 bills. Another box has some $10 bills. Another box has some $5 bills. And another box has some $1 bills. And so the host tells you, you can take 40 bills from one box, 27 bills from another, and 18 bills from another, and 7 from the last one. But you get to pick which one you take which out of. So then, you know, of course, you want to take the most bills out of the most valuable box. And then the second most bills out of the second most valuable box. And that's, etc. And so that's basically what rearrangement is saying. So, you know, that's that. You can use this to prove something called Chebyshev's inequality. And another thing that rearrangement can tell you is that the worst way to do it is to pair them up in reverse order, which is also, I guess, pretty obvious. Okay, enough of the talk. Let me do some problems. But yeah, you can look up stuff. But you can also look up Bernoulli's inequality and other stuff. Well, yeah, Maclaurin's inequality, Newton's inequality. You know, there are a lot of things. But oh, one more thing that is actually one thing that you should really know. This is like up there with AMGM and Cauchy-Schwarz, I would say, in importance. Almost. Is power mean. It's a generalization of AMGM. Basically, it says, to avoid getting into any trouble, I'll take some, let me call it positive reals. So then you can define a function for any real number lambda that isn't 0, or for any real number x, we'll take sort of the x power mean, I guess, which would sort of be just like take each number to the xth power, take the arithmetic mean of those, and then take it to the 1 over x power, which is basically the same as taking the xth root. For any x not equal to 0, for x equal to 0, you take it to just be the geometric mean, it turns out. And so what power mean tells you is that an example of a power mean would be for x equals 2, you get this. Just the square root of this, like you take the squares average them, and then take the square root of that. And this in particular is known as the quadratic mean, or sometimes the root mean square. Or another example could be when x is -1. And notice, when x is 1, you just get the standard old arithmetic mean. When x is 0, you just get the geometric mean. When x is 2, you get the quadratic mean. When x is -1, you get what is known as the harmonic mean. You basically take all the reciprocals, average them, and then take the reciprocal of that, so it looks like this. This is the harmonic mean. So now what power mean tells you is that, let me just abbreviate the x power mean of numbers by Pm sub x of them. So let's say I take some numbers and their x power mean and their y power mean for some values x and y, where x is greater than or equal to y. Then the power mean inequality tells you this. So a simple example could be, for example, that you have for positive reals a and b, you have this. The second power mean is greater than or equal to the first power mean, is greater than or equal to the 0th power mean, is greater than or equal to the negative first power mean. So I think that to have equality, you would either just have to have x equals y or have the ai equal. I'm not completely sure about that. You should probably look it up. And you can probably just look at the handout. But yeah, you can look at the handout when we post it. So yeah. So this is an example of power mean. And you can use this to handle some things. In particular, and this holds for however many variables. And so this can be useful to maybe handle some things that you wouldn't want to handle with just Mgm. So that's power mean. And for things you wouldn't want to handle with AMGM, Holder's inequality is also good. But again, that's outside the scope of this class. But if you want to do more, maybe you can look it up if you're really gung-ho on inequalities. But okay, enough talk about all that. It's time to actually do some problems. So here's a problem. This one is, so let me give you some examples of using these problems. So here's a problem. Bad marker. Go in the garbage, marker. You do not write black ink on the board. Bye-bye, marker. Okay, new marker. That's not so great either. Let x, y, and z be real numbers. Prove that x squared plus y squared plus z squared is at least xy plus xz plus yz. So how do we prove this? Well, this is an example of, there are multiple ways to prove this. Let me show you some ways. So one way to prove this is just to notice that this left-hand side minus this right-hand side, it's just 1/2 of x minus y squared plus x minus z squared plus y minus z squared. If you just expand this, that's exactly what you would get. The left-hand side minus the right-hand side. And so it's at least 0 by the trivial inequality. Another way to prove this would be to notice that it's this. Like, we know this by power mean. Or actually, this would only work if they're positive. But assuming they're positive, then you would know this by power mean. And so you would know this. And then it turns out this is just equivalent to this, if you just do a little algebra because of this identity. Like if you do a little algebra from here, you can get this because of this. Another way to get this that I've seen that doesn't need to assume they're positive is actually, you can rewrite it in this form is what we want to show. And it turns out this is just Cauchy-Schwarz. If you apply it like this, 1 squared plus 1 squared plus 1 squared times x squared plus y squared plus z squared is at least 1 times x plus 1 times y plus 1 times z squared. And this gives you exactly this, which gives you this. And so you can get this as before, is another way I've seen. Another way you could prove it could be, I guess I've seen perhaps that you could use the rearrangement inequality, because this is symmetric in x, y, and z. So like if you switch x and y, or you switch x and z, or you switch y and z, it's the same thing. You can see. So we can assume without loss of generality. With this without loss of generality means basically we assume this one case. And all the other cases are similar. Or we can just, like, if we prove it for this one case, we've proven it for the whole thing. And in this case, you can just assume that x is at least y is at least z because of the symmetry. If we've shown it for this case, you can show it for every other order by just reordering them. By just doing the same thing, but like in a different order by the symmetry. And so what I'm going to do is I'm going to apply the rearrangement inequality like this. I'm going to take the sequence, x, y, z. So if I write it like this, then the products term by term are x squared, y squared, z squared. So when I add them, I get this. And these are in the same order. So let me keep the x, y, z on the top, but let me rearrange it to give me this. What if I write it like this now? And I get x, y, y, z, z, x, which is the same terms as this. And so by rearrangement, this is at least this, which is exactly what we wanted. So this inequality proven, you can see more than one way to prove it. But you can see that this really did, like, sure, we could use rearrangement to prove it, but this really does follow from just the trivial inequality. So, but this problem is, this problem is too well known and probably too easy to appear on any contest. But let me give you an example of a problem that actually appeared on a contest fairly recently that is really just the trivial inequality, but creatively. So actually, before I get to that problem, let me show you something from a recent AMC 12. So the problem is, what is the maximum value of this expression for all real t? And so this looks really weird, but it turns out you can use the trivial inequality, because let's just let 2 to the t be x. Or actually, let me write it this way. Or yeah, if you want, basically we have 2 to the t is x, and let t, yeah, just keep t. So then you can rewrite this expression as x minus 3t times t over x squared. And then if you divide by x squared, you can think of this. Basically, one way I've seen, and maybe this was sort of like what I did in the test, was if you divide by x squared, it's this. So now we have a quadratic function. Like when you have a quadratic function in t to the t over x, if you call this w, say, you have this quadratic function. And so if you want to maximize a quadratic, you can write it, you can just complete the square, which you probably already know. And so when you have this, you can just complete the square. And it turns out if you complete the square, it's 1/12 minus 3 times w minus 1/6. So this is the original expression. This is at least 0. So the expression is at most 1/12. And you can get equality if you just take w to be 1/6. So if this holds, then we have equality. And you can, by arguments with continuous functions, you can prove that you actually can take such t. So the answer is 1/12. And so if you have a quadratic function, you can, and you want to sort of find its maximum or minimum, you can, then you can write it, you can complete the square and then use the trivial inequality. So now let me show you an example. Oh, and someone wrote to me asking me about the previous problem, could you use Muirhead's inequality? Well, for positive real numbers, I guess, or maybe for non-negative real numbers or something, yes, you can use Muirhead's inequality to solve that problem. But like, I didn't really want to specifically get into talking about Muirhead's inequality, though I'll mention it later. But like, you don't need big theorems a lot of the time. But Muirhead's inequality can be useful. You can look it up if you want. But what happened? You can look up Muirhead's inequality. But it's, as I've maybe seen it said, it's just AMGM, but stronger. You don't really need it, but it can be useful occasionally, or at least, but I'll get to that later. But yes, you could use Muirhead's inequality to prove that problem. And, you could use an atomic bomb to kill a flea. So, but yeah, so, and it looks like class probably is going to go over time today to answer another question. But yeah, if you have to go, there will be a recording. Watch the recording, and you can see the handout after class at some point too. So if you have to go, that's understandable because, but yeah, but stay if you reasonably can, because there will be more problems. But if you don't stay, you can watch the recording. But yeah, So here's another example. This problem is actually from a fairly recent Olympiad. This is problem number 1 from the Balkan Math Olympiad of 2014. And you really can solve this basically with just the trivial inequality. So let x, y, and z be positive real numbers. Such that xy plus xz plus yz equals 3xyz. Prove that x squared y plus y squared z plus z squared x is greater than or equal to 2 times x plus y plus z minus 3, and determine when equality holds. And notice, this problem asks you to determine when equality holds. So sometimes problems on inequalities on Olympiads do ask for that. And so if they ask for that, then you should include a brief argument saying when equality holds. But but other times it's just prove this inequality. In that case, if the problem doesn't say determine the equality case, then the assumption is you don't have to prove the equality case. But if the problem says to, then you should say something about it. So think about this problem for just like a minute or two, and think how you might use the trivial inequality. And then but you probably won't solve it because it's kind of tricky. And then in a minute or two, I'll show you the solution. Okay, so let me show you the solution. It's pretty short. So notice this equation, since they're positive, it tells you that 1 over x plus 1 over y plus 1 over z is just xy plus xz plus yz over xyz, you know, with the commutative addition, whatever, which is 3. Okay, so this 3, we can rewrite the equality we need to prove, the inequality to be shown, by bringing the 3 over here. The problem is, and then replacing 3 with 1 over x plus 1 over y plus 1 over z. The problem is equivalent to this. And now look, we have this. X squared y plus 1 over y is at least 2x. Why? Well, one way is just to think of it as AMGM. The arithmetic mean of those two terms is at least their geometric mean, which is x. But you can really think of it as just the trivial inequality, because this holds if and only if, you know, this is equivalent to this just by multiplying by y, which just tells you xy squared minus 1 is greater than or equal to 0, which is true. So we know this is true. So we know this is true. But similarly, you can just do exactly the same thing for y and z, and for z and x. And just add these up, and you get the desired. So we have shown the inequality. And since the problem asked when equality holds, we should mention that. So since we have each of these equalities, for equality to hold in the whole problem, we would need equality in each one. So we see that for equality to hold in this, that's if and only if xy minus 1 is 0. And so we would need this and this. So if equality holds, we would need all 3 of those things. And since they're positive, you can easily check that you would just need x equals y equals z equals 1 to have equality. And you can check if that actually is an equality case. It satisfies this, it satisfies this. You can solve this pretty easily for positive real numbers. And so you would need 1, 1, 1 to be an equality case, and you can check it really is. So the equality case is just x, y, z equals 1, 1, 1. And so we've solved the problem and handled the equality case. So let me tell you about, but now, you know, we should think about AMGM some. So here's a problem. I think this was in the book Proofs Without Words, but we're going to prove it with words. It's basically just for any positive real number t, prove this. And you probably could prove this without words as something like, you could take like a right triangle or something, and like let this be t and this be 1, and then this is 1 over t, and then like if you draw this, this is also 1, and then like this is the length of the chord is at most the length of the diameter or something. Maybe that's probably, the book probably says something like that. But and you could do a proof of AMGM along the lines of this. I think that's in one of those books. But yeah, I think some sources, you could even prove that whole mean inequality chain as it can be known using AMGM. It's like what I've seen, something like this. If I take a circle on a diameter with length a plus b, a, b, and this is, you can see by geometry, this is a plus b. This is a plus b over 2. And if that's the center of the circle. Somehow one, I suppose, oh yeah, the distance from the arc midpoint to here, I think, as it's been in those books, would be this. And like if I draw a perpendicular, this distance would be this. So that's something. I think this is, you can probably find this on the internet or in some book. I think it should be in one of the Proofs Without Words books. But yeah, that's sort of a digression. Basically, to prove this, you can just say, okay, AMGM on T and 1 plus T, they're both positive. Okay, so this is at least this, which is 1. So multiply by 2, you have the desired, yay. You could even prove this just by the trivial inequality, just like since T is positive, it's equivalent to this, which is just equivalent to this. So that's sort of an easy example. So for yeah, if you're wondering about proofs without words, it has some nice proofs by picture of some various things. And there's also proofs without words 2 and proofs without words 3 with more proofs without words of various things. You can look it up. Well, you know, sort of, and someone asked if it was all geometry. It's not exactly, maybe geometry is the wrong word to describe it, but there are lots of, you know, nice math pictures. But yeah, that's sort of, again, sort of just a sidebar. So anyway, here's another example. Let's let of a problem. So take W, X, Y, and Z to be positive real numbers. So the problem is, and this sort of relates to what someone was asking about Muirhead's inequality. But you don't need to know what that is to solve this. Prove this. So take a minute or two to sort of understand what that's saying. And then I will tell you how you can solve this using AMGM cleverly. Okay. So yeah, and as someone said, yes, this exponent that's a 4. And one nice thing about this is homogeneous. Both the sides have degree 17. And so basically, let me rewrite this as W to the 5, X to the 4, Y to the 4, Z to the 4, plus similar things for the others. So what I'm going to do is basically, I'm going to write each of these as some linear expression in each of those and then just add them up and it'll work. So it turns out, claim this. Proof so this is saying w to the 5, x to the 4, y to the 4, z to the 4 is at most 5/17 w to the 17 plus 4/17 x to the 17 plus 4/17 y to the 17 plus 4/17 z to the 17. And so the proof of this claim is just, it turns out you can just do this. So this would follow immediately from what's known as weighted AMGM, which you can look up. But I don't plan to discuss that too much today, but you can look it up. But you can actually just get this with regular AMGM, because basically, let's view this left-hand side. We can look at this as a geometric mean, and this is an arithmetic mean. If you write 17, and then just like write 5 copies of w to the 17, and 4 copies of x to the 17, and 4 copies of y to the 17, and 4 copies of z to the 17. Then the arithmetic mean will be exactly this, and the geometric mean would just be this, the 17th root of, you know, all those, you know, the product of all those, you would just get this, it turns out. So by AMGM, you get that big expression. And similarly, you could have this. This term would be a similar thing, but now x would be have a 5 on it. And similar for the y and the z. And then if you just add them up, you get 5/17 plus 4/17 plus 4/17 plus 4/17 is 1. And so all the coefficients, you just add up to 1 and you just get exactly this. So this proves the problem. And so this might have looked a bit strange, but basically, this is sort of a method for a whole general class of problems, which basically just tells you that, like, suppose you have some expression that's like, I guess, sort of a homogeneous inequality. That's just like a bunch of sum of some monomials is greater than or equal to sum of some other monomials. So then sometimes what you can do, this doesn't always work for such problems, but it works sometimes for, and it's an example of what works here, is basically write the monomials on the right side in terms of like AMGM of stuff on the left side. Like write the terms on the small side as AMGM of stuff on the big side. Just sort of force them to be geometric means of the stuff. So we basically just, what we did was we basically just, we just took this and we said, okay, I'm going to force this to be a geometric mean of w to the 17 and x to the 17 and y to the 17 and z to the 17. And then just take them in appropriate quantities to make it a geometric mean. and then just do that for every term and add it up and hope for the best. And so this is sort of an idea behind stuff, and this relates back to a question someone asked me earlier about Muirhead's inequality. And it turns out that Muirhead's inequality is ideas like this. And so for those who know this stuff, this inequality we did earlier, for positive x, y, and z, or I guess you could probably say for non-negative, but I'll just say for positive x, y, and z, yes, as someone asked, it would just be Muirhead on 2, 0, 0, and 1, 1, 0, if you know what that means. With the same idea basically just being the same idea, like write x, y as a geometric mean of x squared and y squared. And similarly, you can do that for each term and then just add it up. For positive real numbers, you could just take the arithmetic, the AMGM, and in fact, this would work for any x, y, because like AMGM would give you absolute value signs, and then any numbers at most is absolute value. So, etc. You can, and then similar for YZ, add. So yeah, but that's sort of the idea here, sort of the intuition. I hope some of that made sense. But let me give you another example of an AMGM problem, and this, or sort of a, not as much like sort of AMGM, but sort of just like doing there's some algebraic work involved, and there's another idea. But I think you will want some AMGM / trivial inequality for this, I guess. So the problem is this is 1983 IMO problem 6. So the problem is, let A, B, and C, you might expect me to say let A, B, and C be just positive real numbers. But actually, let's spice things up a little. This problem has an interesting thing that you can use a neat trick for problems like this. Let A, B, C be the side lengths of a triangle. Prove this. Let me be sure. And determine when equality holds. So take a minute to think about this, but you will want an interesting idea, which I will tell you about, and then I'll show you how to show the solution, but take a minute to think about this. So the idea I was talking about is the idea that when you have numbers that are the sides of a triangle, you can write them like this. For assuming the triangle is non-degenerate for positive real numbers x, y, and z. Because basically you just take this, for example, would be that, which is positive by the triangle inequality. And so this is sort of informally known as the Ravi substitution, I think popularized by someone named Ravi, maybe it was Ravi Jagadisan, someone named Ravi popularized this, I guess. Or something like that. And so let's make that substitution here. And so the problem becomes we have positive reals x, y, and z, and we want to prove this. This, because x plus y minus x plus z is just y minus z, this plus another thing plus another thing. Similarly is at least 0. And so the next thing you do is basically you would just have to take this whole expression with this term and the other two, and you would expand it. And then you would do some calculations, which you could do, but I will just tell you what the result is, I guess. Basically, what the result is that it turns out to be equivalent to just proving this. Or actually, I'm going to do the substitution to go along with this book I have here. An equivalent way of doing the substitution. This is also a pretty good book, the IMO Compendium. It has lots of old IMO and IMO shortlist poems. You could do it like this. And so then this would be some other term, and then you would just do some computation. Not a lot of computation, but enough that I don't really feel like doing it. And so then the problem just becomes this. And then you can prove this. It should be equivalent to this, I guess. To prove this, one way of doing it would just be to think of it as you have this x squared yz, x yz squared, x yz squared, and then you want to prove that it's less than or equal to this. Now, so one way, I guess, I've seen or something that you could finish from here, you could just write, there are multiple things you could do. You could just write like this is at least this minus this. And then make similar things, add them up, and you would get the desired. And you could figure out the equality case, which is this is a less than or equal to. And so you could make similar things and add them up and get the desired result. And you could get the equality case, which I'm not going to do, but I'll just tell you what the answer is. It turns out the equality case is just when x, they're all equal, making the original thing just all equal, according to this book. And I think you could just easily get it from here. Another way you could prove this inequality, if you're really dedicated to doing that method I told you about earlier, I believe it should follow from that method. Because if you take this x squared yz, and you want to write it in terms of some AMGM of these numbers, you would probably want to think of it in terms of weighted AMGM. But like, I believe I think you should have something like this. And this will just be an AMGM, it turns out. Though for stuff like this, you would probably want to use weighted AMGM, which in this case would basically just tell you that this is greater than or equal to like this. You can look it up. And which would just be equal to this. So that's another way. And so, but yeah, basically what you should take away from this is this sort of idea of when you have numbers representing the sides of a triangle, you can do this, the so-called Ravi substitution, like this. Whatever. And you can figure out the equality case, but yeah. On a contest, you would have to, but if it said to do the equality case, you had better do it, but this is class. It's not an actual contest, so you can work it out for yourself. But yeah, as I said, it turns out to just be when they're all equal. A equals B equals C, according to the book. And I think that's right and not very hard, but yeah. It's not, it wouldn't be overly enlightening, perhaps. Not about inequalities, anyway. But let me go on to examples of what you can do with Cauchy. So here's an easy problem, or easy by comparison, of, let's say we have positive real numbers, x and y, with x plus 1 over y is 7. Find the smallest possible value, the minimum value of y plus 1 over x. So think about this for a minute. And you can, or actually, I'll just think for a minute about how you could use Cauchy-Schwarz on this, or how you could solve it some other way. The answer is not 1 1/6. Actually, this was a Math Counts National Countdown Round problem. That someone actually answered that, except it said common fraction. So someone said 7/6, but no, it's not right. They don't have to be integers. They can just be positive real numbers. So, okay, let me show you the solution. One way you could do it would just be you could just write this as just like this, and then you would want to minimize this, which you could do just as like writing it as a quadratic or whatever. But I want to briefly show an example of how you would do it with Cauchy. You could also do this with the inequality, but from that point, you could do it with the inequality between, once you have it like this, you could do it with the inequality between the arithmetic mean and the harmonic mean. But I want to show you with Cauchy, where basically the idea is, let me write it like this. One way, like things I've seen, I guess, would be to rewrite this as Cauchy, because you can think of this as like root x squared plus, you know, so it's at least, so now this is at least the square of when you multiply those together, which is 1 plus when you multiply those together plus 1 squared, so it's at least 4, i.e. this is at least 4. So since this is 7, this quantity, y plus 1 over x, is at least 4/7. And you can have equality. Because to make equality, let's think about the equality case for Cauchy-Schwarz. Basically, if I want to just find some values to make them proportional, intuitively, if I want these sequences to sort, like none of these are going to be 0. So basically, we want the equality case of Cauchy-Schwarz to look something like this for some lambda, and this would you'll want x and y to be reciprocals. So 1 over y will equal x, and so you can just do some algebra because then x plus x is 7. So you'll want x is 7 over 2 and y is 2 over 7, and that will give you 4/7. So it's at least 4/7, and 4/7 can be achieved, so that's the answer. And in general, when you have a problem like this on an Olympiad, not just like an algebraic inequality, but like any type of problem that tells you that asks what is the maximum value, or what is the minimum value, or I even prove that this is the minimum or maximum value of something. But when like often you'll see like what is the minimum or maximum value of something, not just inequalities, maybe, you know, combinatorics or whatnot. A proof on an Olympiad would be what of such a problem is you should say what the answer is, prove that you can achieve the answer, and then prove that the answer is actually a bound. So like for a solution to this problem, I needed to say this is at least 4/7, and there is a case where it equals 4/7, thus it is the minimum. If I only said it's greater than or equal to 4/7, that wouldn't be a complete solution on an Olympiad. Of course, for math counts, you don't have to give a full write-up, but for the USAMO or the USAJMO, you had better give all the details if you don't want to lose points, basically. And so this Cauchy way is a nice way of thinking about it, that you can sort of almost do it without writing anything down. So if someone was wondering how I would do this problem, I think this is sort of one of the nicest ways you could do it. So let me give you another example. Here's a more difficult Cauchy-Schwarz example. So This problem is USAJMO 2012, problem 3. So the problem is, let A, B, C be positive real numbers. Prove, let me make sure to get this right. Prove this. So take a moment to think about how you could apply Cauchy-Schwarz to this problem in the form of T2's lemma. And then I'll tell you the solution. Oh, so if this is blurry for some people, this says a cubed plus 3b cubed over 5a plus b plus b cubed plus 3c cubed over 5b plus c plus c cubed plus 3a cubed over 5c plus a is greater than or equal to 2/3 a squared plus b squared plus c squared. So, okay, you've thought about it a little. And so there are multiple ways of doing this problem. In fact, one solution, I guess maybe one of the sort of official solutions, basically would just directly prove this. I believe, if I'm remembering correctly, it's something like this is what it proves, I think. And then just immediately get the problem from that just by adding up it cyclically. But like, so you could solve this problem by just sort of saying, let me find suitable constants, you know, lambda and mu to prove an inequality like this, and then like find the right constants. Maybe you would use a little bit of calculus to like take the derivative or something. But let me show you a nice way using T2's lemma. And the solution I'm about to show you, I think it's on Evan Chen's inequalities handout, which is on his website, which if you want more inequality goodness, you can go to his website, web.evanchen.cc, and then look on the handouts, and you can see an inequalities handout. Lots of good handouts on that website, lots of good math handouts to read if you want. So the solution on that handout, as it's presented there, is a nice way of using T2's lemma. So let's just take this expression just by itself. So this looks an awful lot like T2's lemma. So we have some fractions, and then we want, and some powers in the numerator or something. If you just try to use T2's lemma in the most naive way, you're not going to like what you get. But you would get some like 3/2 powers, and I don't think the inequality you would get would be quite strong enough necessarily to give you what you want. But let me do something weird. Let's force these to be let's force the numerators to actually be squares. I'm going to multiply the numerator and denominator of this fraction a cubed over 5a plus b. I'm going to multiply by a. So now it becomes a to the 4th over 5a squared plus ab. And same for the other two. So we have b to the 4th over 5b squared plus bc, and c to the 4th over 5c squared plus ca. Now apply T2's lemma, because we can view each of the numerators as like something squared. Everything is positive, so T2's lemma is fine. The denominators in particular are all positive since a, b, c are positive. So by T2's lemma, this is greater than or equal to a squared plus b squared plus c squared plus 5, like the sum of the denominators, 5a squared plus ab plus 5b squared plus bc plus 5c squared plus ca. And now we know that ab plus bc plus ca is at most a squared plus b squared plus c squared. This was the problem we did earlier. So when I add 5a plus b plus c, a squared plus b squared plus c squared to both sides, it's still true. And so taking reciprocals, since both sides are positive, that would flip the inequality sign, and then multiplying through, basically using that, I would get that this is greater than or equal to this. Then a squared plus b squared plus c squared over 6a squared plus b squared plus c squared, and then just canceling, you get just this, 1/6 a squared plus b squared plus c squared. And then you could do a very similar thing with the other terms, the 3b squared, the 3b cubed over 5a plus b. You would just do the same thing, 5ab plus b squared, b to the 4th now. And similar thing, do T2's lemma in a similar way, and you could get that the other term is at least 1/2 a squared plus b squared plus c squared. Adding, you get the desired result. And so that's how you could use T2's lemma to a nice application. So yeah, Cauchy, Schwarz, T2's lemma, good things. So now one more problem, and I guess this will be the last problem of today's lecture. So this problem is And this sort of is an example of how you can use power mean. So this problem looks kind of ugly. This problem is 2009 IMO shortlist A4. So it was the fourth problem on the algebra section. And so the problem says, let A, B, C be positive real numbers. It actually says be positive real numbers, but I'll just abbreviate it by just that. Such that AB plus BC plus CA is less than or equal to 3ABC. Prove that this big ugly thing, the square root of A squared plus B squared over A plus B plus the square root of B squared plus C squared over B plus C plus the square root of C squared plus A squared over C plus A plus 3 is less than or equal to the square root of 2 times the quantity, the square root of A plus B plus the square root of B plus C plus the square root of C plus A. And so think about that for just a minute, and then sort of just drink it in, so soak in what that's saying, and then I can show you how to solve this using the power mean inequality. So think about that very briefly. Okay, so maybe you thought about it for a minute or so. So what do we do? So first of all, I'm going to prove this and this is following along with the solution on the IMO website. So first of all, I'm going to show you this. The square root of A squared plus B squared over A plus B plus the square root of 2AB over A plus B is less than or equal to the square root of 2 times the square root of A plus B. So notice, this is just saying, if we call this X and Y, since the sum of A squared plus B squared over A plus B and 2AB over A plus B is A squared plus B squared plus 2AB over A plus B, which is just A plus B. This is basically just, it's enough to prove this. And this holds for any positive reals X, Y, and Z. I mean, sorry, X and Y. You can basically, one way to think of it is that it's equivalent to saying it's equivalent to writing this. And this is just power mean, because this is the 1/2 power mean, and this is the 1 power mean. So this is true. So then another claim I'm going to prove. So we know this, and then you can prove a similar thing for B and C, and then for C and A. Okay. Then another claim I'm going to show. So basically, let's look at where we are. If I could just replace each of those terms with those, which might not be enough, but it turns out this is going to be enough, then it would be sufficient to prove this. So it would be sufficient to prove this, because if we prove this, then I can just take these three inequalities, this and the symmetric thing with the B and C and the C and the A, add them up, and then just replace these three terms with a 3, because that would make it, that would be going downward, less like this would be less than or equal to, you know, the other thing, and so this would imply the problem. So let's prove this. So if we have I'll call these numbers P, Q, and R. Now notice this inequality, it's sort of not homogeneous. Each of these terms sort of has degree 1/2, while this has degree 0. And so we're going to want to make use of this condition, which is also not homogeneous. So we're going to want to incorporate this condition somehow. So bearing that in mind, I'll just sort of tell you what to do from here, especially because it's getting pretty late. So you can just write it as 1 over P squared is A plus B over 2AB, which is 1/2 1 over A plus 1 over B. And now, writing similar things for Q and R, you get this. 1 over P squared plus 1 over Q squared plus 1 over R squared is at least 1 over, is equal to, 1 over A plus 1 over B plus 1 over C. Which is at most 3 because of this. Just divide by A, B, C and see what you get. So we have that 1 over P squared plus 1 over Q squared plus 1 over R squared is at most 3. And we want to show that P plus Q plus R is at least 3. So let me erase this. So it turns out that you can just view this. So basically, we have that P plus Q plus, we want to show this, the arithmetic mean is at least 1. But this looks sort of like we're raising PQR to the -2. So when I have this expression, P to the -2 plus Q to the -2 plus R to the -2 over 3, that's at most 1. So when I raise it to a negative power, it's at most 1 and it's positive because A, B, C are positive. So when I raise it to a negative power, the result is at least 1. So when I do this, it's at least 1. because that's how negative powers work with inequalities, basically. But now this is the -2 power mean. So using this, 1 is greater than or equal to -2. By power mean, the 1 power mean, p plus q plus r over 3, is greater than or equal to the -2 power mean, which is greater than or equal to 1. So p plus q plus r is at least 3. So we've shown this. We've shown that square root 2ab over a plus b plus similar things is at least 3. And now we're done. Why? Well, take this inequality, write down 2 others like it, you can imagine. You know, add and a third one for this. Add them all up. And then the sum of all those is at most the sum of all these. But then this sum is at most the sum of all these, because like this sum, the sum of those 3 square roots is at least 3. And so this sum is at most this sum, which is just that. So we've shown the problem. The proof is complete. So yeah, okay, it's 5:01. So thank you all for staying for so long. There will be a recording. The handout, I think, will have lots and lots of problems on it. And so you can use lots of these theorems or just some algebraic manipulations or some combination of both with some cleverness. So yeah, nice theorem. So theorems have applications like I showed you. So hopefully this was helpful. So, and you can see Evan Chen's website for his inequalities handout and other good math stuff. So thank you all for attending the class. So, you know, if you have any questions, you know, you can email us at mathdivulged@gmail.com. You can go to our website, mathdivulged.com. So hopefully this was helpful. You can see the recording. You can look at the handout pretty soon, I think. And so, yeah, best of luck on the USAMO or USAJMO if you're taking it. So thank you all for coming. And I guess I'll stop there. So thank you all. Bye-bye.